approximation. This is lecture number 2. Potential approximation. Can you read this clearly?
Yes, sir. It's at the very top of the frame, but you can see it.
Okay, very good. Correct. So last time, this is lecture number 2, but in lecture number 1, we covered the various topics. We did the background. And in the background, we covered the density of states. I repeat, we did the density of states. Let me just tell you what the density of states looks like, say for a one-dimensional solid. Okay, so if you have a Hamiltonian, which is simply minus t sum over I not equal to j nearest neighbor ij. That is to say, I take the diagonal term to be 0. Okay, so that Hamiltonian, we can call it as something like h0 or something, right? Or something. Right? This is the Hamiltonian with only diagonal term epsilon equal to 0, nearest neighbor. If you are in one dimension, in 1D, the density of states below 0z would look like what? It would look like 1 over pi square root of 1 minus z by 2t the whole square. This is how the density of states would look. So when z is equal to 2t or minus 2t, the density of states blows up. The density of states has a minimum when z is equal to 0. Okay? So the density of states would look like this. Okay. I'm sort of repeating the obvious to you. Okay. The obvious thing is that it will be 2t to minus 2t. What's on the y-axis? It is the density of states. It is the number of states per unit energy interval per unit site, per site. So this is per unit energy interval. By definition, it is dimensionally correct. Okay. It agrees with the definition as far as dimensions go, and it looks like this. Let me just plot it. Looks like this. That is the density. What is the Green's function? You said, I've forgotten, sir. We did it long ago. We did it 4 lectures ago. The Green's function would be, for example, if I did the Green's function, the diagonal part of the Green's function, the diagonal part would be equal to, say, minus I sum over pi square root of z squared minus 1. Something like this. The Green's function is purely imaginary. Or it is the imaginary part of the Green's function. Right? So, am I right? I'm just trying to see if I'm right. Okay. So just look it up. I think there is something like this. Yes. So basically, the Green's function will mimic the density of states. The imaginary part of this will mimic this. The real part of this, basically, there is no real part inside. It's only outside. Okay. Can I just take a look? I don't want to be wrong on this now. It is, I was wondering what I was doing wrong. It is something like this. Can I just correct myself? 1 minus z by 2t the whole square. That is how the Green's function looks. This is partly from memory and partly by guesswork. Okay. The Green's function the imaginary part should agree with this. And when z is greater than 1, so this denominator becomes imaginary. The Green's function is purely real, outside the band. So this is inside the band, and this part is outside. Is that clear, or is there any question on this? Okay. So this is from memory. Okay. This is also from memory, but I'm only reminding you. And the imaginary part of this should be equal to this. Often, you take 2t to be equal to 1. You just set the scale. So in that particular case, you get the density of states is from -1 to +. Okay. So it's like scaling it. Then we went ahead and we discussed the introduction. What did we do in the introduction? We said, what is it that the CPA is all about? The CPA is an effective medium theory. You have so first we define a substitutionally disordered system, which was defined like this. Okay. Okay, I write it down again. Minus t sum over I not equal to j nearest neighbor. Okay, I j. This is my Hamiltonian. Okay, it is the simplest possible Hamiltonian you can think of. It has got substitutional disorder at the site I. You have a lattice, but at the lattice point, you can have either A type of atom or B type of atom. You could have copper or you could have nickel. If you have gallium aluminum arsenide, then on the arsenic site, it is perfectly ordered. That is the anion site, the cation site. Okay, that is where gallium sits. It could be either gallium or aluminum. So that is how you define it. You take the off-diagonal term to be ordered. Why do we do that? There is no God-given thing that has to be ordered. Okay. The only thing is we want to do the simplest possible model Hamiltonian and see if we can make some physics out of that. Okay, we can extract some physics from it, some insight from it. Okay. So what the CPA is about, what the coherent potential approximation is about, is to replace this by an effective medium. Okay, I can replace it by saying that instead of this, I have a sigma sum over I. The other term is just continuous minus all this. Is that clear? Minus the off-diagonal term. Okay, and then we have to get this. It can so happen that sigma can become energy dependent. We haven't yet done it, but I'm only giving you a preview of it. Simply a preview of what we expect, what to expect. And so you replace this by an effective medium, get a prescription for sigma. The other thing is, what are we looking for? So the introduction will foreshadow what we are going to look for. If we have two dissimilar type of atoms, do I get a split band or do I get a merged band? And then what is the Lifshitz limit? So we reviewed some of it in the introduction. Then we went and did the third thing, the virtual crystal approximation, the VCA. The virtual crystal approximation, in which we say that the simplest possible thing I can conceivably do is to take the sigma z and make it equal to Ca epsilon A plus Cb epsilon. That is to say, Ca and Cb are the concentrations of the A and B type of atoms, say copper and nickel. Okay. Ca plus Cb is of course 1. Okay. And epsilon A or epsilon B is other two. हेलो अभी हम क्लास ले रहे हैं, अभी इसके बाद हम देखेंगे सिर्फ 1 घंटे के बाद. हाँ अच्छा, हम देख लेते हैं. हाँ, आपको फोन कर देते, नहीं मिला होगा तो मैं फोन कर दूँ. ठीक है, थैंक यू. Is this clear? So that is what we did for the BC. We said that we average the sigma. You don't average the density of states. The average of the density of states is not equal to the average of this quantity. With that, let me continue. But before I do that, are there any questions? Yes, Mr. Prithvitosh?
No questions from me, sir.
Huh?
No
Yes?
questions from me, sir. I don't have any questions.
Okay. All right. What about somebody else? What about Rishabh Varma?
No, sir.
Okay. All right. So let me continue. Some amount of formalism is necessary. So we will do the formalism and then we'll do what I would call as exploring the CPA. To carry the formalism forward, we have to deal with Green's functions. If we deal with Green's functions, then there is an issue, and the issue is I shall have to review some things for you. But there's also an issue that you will be expanding things and you'll be expanding operators. So I remind you that there is a Taylor expansion which looks like this: 1 minus x, 1 plus x. Okay, right? We extend this to operators also. So if there's an operator like 1 minus AB, I will write as 1 plus AB plus AB, AB plus AB, AB, AB. Okay. And we ask no questions about the validity of this expansion. Okay. Also, it is worthwhile to remember that AB inverse is equal to B inverse A inverse. Okay. So in what I carry through, you can at a time when you have some leisure check that I have not violated anything like an operator identity. Right? I have not said things like AB is equal to B. That I will not do. But I might go a little fast and I might not probably explain the whole thing to you. You should work this out for yourself and ensure that what I do is correct. So you have the Green's function, say, if there is a Hamiltonian, in our case, our Hamiltonian is, let us say, 0 plus, where my H0 is equal to minus T sum over I, not equal to J, nearest neighbor. So the H0 is the off-diagonal term which is ordered, and the V is the diagonal term which is disordered. Right? So the Green's function Z minus H. So there are actually various levels at which I will do it. 4.1. Let me call it 4.1. And you have to remember that this is an operator. This Z is a number, but associated with the Z is an identity operator. But it's also an operator in that sense. Let me just erase this. G0. That is the ordered Green's function. This is also, that is 1 over z minus h0, by the way. Not the whole thing. This whole thing is 1 over z. This is also equal to t0 z. And now I do the Taylor expansion of this. So the Taylor expansion would be what? G0. The z argument here, the z argument is assumed. It's there. All of the 7. Of course, I can truncate this. I can say that z is equal to g0 plus g0 v into g0 plus g0 v plus g0. Right? And all of this is nothing but this g. Okay? So I have this g0 plus g0. If I stop here in this perturbation expansion, and I don't take any of those terms, if I stop just here, that is what you do when you do the Born approximation. So when you do the Born approximation, I remind you from your textbook, the psi is equal to phi with integral something like g0 into phi or something like that, into v. It has to be psi, but instead of psi, if you make it phi, I mean the free, what is it called, the free particle wave function, then it is just the Born approximation. It is the Born approximation. So if you were to stop, how should I say, at this point, take no further terms, I will get the Born approximation. If, however, I rope in here, okay, I get an expansion, but here's the g again. So now if I want to average, if I say the average of g, G0 is already ordered, there's nothing to average in G0. G0 doesn't have to be averaged. And if, and that is not right, perhaps, if I say the average of a product is equal to the product of the averages, then I have G0 plus G0 in that case, and I think I have a little struct for space here, so I'll use this part of the blackboard. In that case, what I get is my Green's function is simply G0 into 1 minus G0 into. That's how the Green's function. So I have what is called, if I were doing many body theory, I would say I've decoupled the equation. And if you're doing averaging, all that I've done is I've taken the product of the averages to be equal to the average of the product. So if I do this, then the average of V, okay, for a single site approximation is simply CA. Then I'm all right. If I'm allowed to do this, okay, then I'm fine. I'll get the VCA. I'll get the virtual crystal approximation. I can do better than this. That clear? I can do better than this.
Sir, not really. Under what circumstances can I take the average of the product to be equal to the product of the average?
No, you can't. I'm saying if you do. If you do, then I'm saying. I'm not saying this is right. What I'm saying is you can do better than this.
Okay, so taking that is equivalent to taking the virtual crystal approximation. And they're
Yes.
both equally wrong or equally right.
Yes. may not be all that bad, but it certainly doesn't. It raises some issue that perhaps one can try and do better than this.
Okay, sir.
All right, thank you. This is one good thing about the blackboard presentation is that when I erase it, I slow down. Okay, it gives you time to think. And I do my erasure. If I were going to do an online presentation, I would be stopping. But I would go immediately to the next one. Okay. So if I want to do better than this, so I'll call this 4.2 now. Okay. I change my perspective just a little bit, okay, but in a very important way. What I say is, let me erase this. I'm not, otherwise I'll have a lot of clutter. Okay, I'll have H is equal to sum over I, epsilon I minus T, sum over I not equal to 3. At the risk of repetition, I write this substitutionary disordered Hamiltonian for the 10th time. Epsilon I is disordered. Okay. It can take values like epsilon A or epsilon B, okay, with concentrations CA or CB, respectively, of course, CA plus CB equal to 1. Now my ordered Hamiltonian, so-called ordered Hamiltonian, which I call H0, is the following. It is the effective medium Hamiltonian. I say that this is the Hamiltonian which represents this. So what is the impurity? What is the perturbation? The perturbation is the following. This is the perturbation. That is to say, I remove sigma and I put epsilon I. Remove that sigma and put epsilon. So what pictorially what it means is here I have a lattice. Let me use another chalk here. The first one is a lattice like this. Okay, so it has got atoms like this. Okay, all kind of A and B types of atoms. This is epsilon A, this is epsilon B. So the square is an epsilon B, the circle is an epsilon A. What is this Hamiltonian? The ordered Hamiltonian that I do, so-called order, it's an effective medium. Okay, it is like this. Okay, it has, let us say, only this. Etc. Okay, it has only sigma. And what is the perturbation Hamiltonian? The perturbed Hamiltonian? Each site, you put exactly what was there. Okay. The perturbed Hamiltonian or the perturbation. Okay, I don't know if there's a square There is a circle and there's a diamond. What is the other symbol I can use? Cross. So let us use a cross. The cross, this cross will represent, say, epsilon A minus sigma. Okay. And another colored cross like this. This would be like here is epsilon B minus sigma. Here there was epsilon A, so it will be a cross. Here there was epsilon, so here it will be a let's see. Something like that. Okay. So that is the idea. Pictorially, this is what we are doing. We are replacing this by an effective medium, and I want this sigma. So in the case that this truly represents this medium, okay, this average should go to 0. So there should be no perturbation. Is that clear? That is the idea. I repeat it. If this effective medium truly represents the original medium, then this perturbation should vanish. Allow me to continue. So now I have H, the Green's function g of z is equal to G0. So remember what we have done already, right? G0 plus G0, okay, V G0 plus G0, V G0. Right. This expansion will work perfectly well. You know, this is got nothing to do with what we are doing here. Only thing is the V now represents this, the G0 represents this.
Yes, sir.
Bolo.
Yeah. Why does the V have a transfer term? Why is the transfer term in both the H0 in all three Hamiltonians the same?
The what?
The T term, the nearest neighbor interaction.
This is our assumption. That we are taking the off-diagonal term to be ordered. We are not taking any disorder in the off-diagonal term. Okay. We have already taken it by the assumption. Okay. You can say, what if I make this disordered and make it inside Tij? That can also be done. That would be, conceptually, it would not be a great advance. If you can do this right, you can do that also, I can tell you. Okay. But right now, we want to do the simplest possible. You might say, why is the Ising model such a great model? When you're doing something like statistical mechanics. It has got only nearest neighbor. It has got spins which can only take values plus or minus 1. So why not have all kinds of spin? You know, I've heard of Bohr magneton and all that kind of nonsense. Okay, I can have many other things. I can have cos theta, that cos theta factor, and can be space quantization. All that can happen. Yes, but can you? The question that you're being asked is the following: if I take the simplest classical interacting Hamiltonian, that is the idea, then can I do that exactly? Can I get insight from that? And the answer is yes. The whole history of the Ising model, starting from 1921, is a testament to the fact that if you can do this Hamiltonian right, you can extract a whole lot of good physics from it. Similarly here, if you can do this right, then you will get some insight. The issue is, how should I put it? There's a very big word for it. It's called universality. Universality in the sense that if I can understand the Ising model right and the phase transition in it, I can understand phase transitions in real systems, second order phase transitions. That is what it is. It's a universal model. Similarly, this substitutionally disordered model is a universal model. It has some universality. Yes.
No, so that explains why it's same for all the sites in the H in the first origin in the Hamiltonian H and in H0 as well.
Asking this question, please. Your name?
Prithvitas.
What is the question?
The question is, V was diagonal in the previous thing which we did. Here it has off-diagonal terms as well. So the whole H is equal to H0 plus V does not hold anymore. Because now both of them have the off-diagonal term.
Oh, okay. So what would you like to do? I mean, tell me what you want to do. You don't want this?
Okay, I'd like to remove the off-diagonal term from V. Okay.
Yes, sir. Because H0 plus V should give us the H, right? That's the, yeah.
Correct. Okay. So we have this. So okay. Granted. Was that the question? Yes, I removed. Yes. Let me come to it. I'm a little confused, but I think this question is. Yes, there's no T there. That's correct. So you have something like this. I'm now expanding this in a slightly different way. And if you are familiar with the impurity calculation, you'll probably guess what I'm going to do next. What am I going to do next? Yes, Mr. Let us see. Who wants to answer this question? Aparna, what would I do next?
So you rewrite the B plus PG not
What is that?
so whatever is written on inside the brackets you rewrite.
That is equal to what? That is equal to the T matrix. Right. So if GZ, if I do average of GZ, correct, then this is equal to G0 plus G0, because this is already average. This is an average quantity. Are you with me up to this point? So this is already an average. So if G0 is really a good representation of G, what happens to T? If G0 is really a good if this is really a good representation of this, okay, it can't be an absolutely 100% representation of it, but if it's a faithful representation of this, what will happen to the T is that the T will vanish. The T will go to 0. Okay. Exactly. It will go to 0 exactly in that sense. If this represents this. Are you with me up to this point? Okay. Right? A little bit of extra work or formalism is now required to continue. Okay. I could have written down, this is exactly, how should I put it? This is very similar to the idea of Brugman. You remove something and you put it there, and if it is a faithful representation, then it is 0. That medium, any kind of replacement of sigma effective by sigma 1 or sigma 2 at random should be give you a 0 result, 0 fluctuation. So let's do a little bit of extra work as needed, not too much. So can I erase this? You have it all with you? Students?
Yes, sir.
Yes, sir.
I can remove it. So just remember it, because I do for you to make sure that you. I'm going to erase this. Okay. So let me look at T. T is equal to V plus. Sorry about that. V G0 V plus V G0 V. You don't have to take all of this. I think you should. In fact, if you're taking notes, then you take this. How many times have we did it? Correct? Am I right? Convinced? I will expand. Okay. So then I do what is called a site representation. I write my T, I decouple my T and write it as 1 over C sub QI. The QI, and I think I'll leave some space. So if you'll allow me, and this QI is equal to sum over VI plus VI G0 sum over M Q. So all that I'm doing is that since I'm doing a site representation, the V is also sum over I, VI, and this is also VI, and there is a G0T, so the T I write as sum over MQ. Are you with me? Is this clear? The Saloni? Mandloy.
Yes, sir, this is fine. Yes, sir.
Wonderful, wonderful. I'll just take a sip of water. So now I continue. I write this as VI plus VI G0, the QI plus VI G0 sum over J not equal to I QJ. हेलो हाँ कहिए जरा मैं अभी क्लास हाँ कहिए तो क्या हुआ हाँ क्या हुआ क्या मुझे बता दीजिए हाँ तो क्या हाँ हाँ अच्छा हाँ हाँ ठीक ठीक है तो हम शाम को बात करते हैं कितना बजे तक ठीक अभी क्लास ले रहे हैं Good. I'm getting all kinds of important calls while I'm taking this class. Okay. Are you comfortable with this? Well, J and decoupling. So I'll take the QI on this side. My QI is equal to VI. Okay. Are you comfortable with this? Plus VI 1 minus G0 VI G0 sum over J not equal to I QJ. Okay. Right. Having understood this step, okay, we don't understand the logic behind it. I will tell you the logic behind it in a little while. So what you say, yes, algebraically I understand the step. What are you trying to do? So the way I would respond is just hold on for a few minutes of patience, and I'll tell you why I'm doing So first of all, it must be clear to you that if I have a matrix like this, T, okay, I could have taken the T over here and I would have gotten V is equal to 1 minus VG0 in the abstract. I would say in the abstract Hilbert space. Now I've got a site or a one-year representation here, okay, in which it looks like this, so that T is equal to capital V over 1 minus VG0 is being replaced by small v 1 minus G0V. Okay. This thing would have been the same as T is equal to capital V over 1 minus G0. Okay. And this has the same structure as this. So this is called a single site T matrix. Okay. That's why I said site representation. It's a single site T matrix. So I get Qi is equal to Ti plus Pi G0 sum over J not equal to I Qj. This entire thing I'm calling Pi. It is called the single site T matrix. And this kind of an expansion, okay, was actually first effected by Mel Lax in 1952. It's called the Lax expansion. Okay. Let me continue. So you have this. Okay. So now what I do is I do something equally interesting. I note that there is a certain iterative character to this expression. The same kind of iterative character which exists for Green's function. I have Qi, Ti, G0, Qj. So instead of Qj, I'll write Tj. Okay. And then I'll continue in that fashion. So I'll write a single site expansion for this. So this is Pi plus Pi G0. Okay. And then instead of Qj, I'll put something like Tj. Okay. Sum over J. Let me put the sum here. J not equal to I Tj. Okay. Plus, I will go out of the blackboard there, so I'll put the plus here, sum over Pi G0 Tk G0 Tj. No, I can just keep changing the indices. This is I, and I'll put a prime here. Plus, okay. So when I do the expansion and I repeat Tj over here, J is not equal to I. When I do an expansion like this, all that it says is K is not equal to I, J is not equal to K. So successive indices are not equal. It's not that I can be equal to J in this expansion. Okay. Is that clear? Okay. I can have an I being equal to J or I. So whatever I want to call it, I can interchange K and J. But any successive indices, they are not equal. So the summation of prime implies successive indices are not equal. So we have that average T should be equal to 0. If my H0 is indeed a faithful representation of the original Hamiltonian, the T matrix should be 0. But this T is nothing but sum over I Qi equal to 0. That means to say I must have that Qi is equal to 0 because these are independent sums. This is Qi Q1 plus Q2 plus Q3 plus Q4. So this you can then say that each site is on each side the so-called Qi operator, this least of a quantity should be equal to 0. And if this is 0, it implies, look at this expansion. If this is 0, then I would have something like this Ti must be 0. Okay. Then I would have something like this must be 0. Then I would have something like this must be 0. Correct? Now, in this first term, since I is not equal to j, now this is the key point. If I is not equal to j, okay, then I could have this is equal. Since I is not equal to j. These are independent sites. So I can justify that expansion. But here, I cannot justify this expansion. This does not mean this. Okay. If, however, okay, I ignore these, I say that, okay, look, these are at least successive sites are not equal. So perhaps I will make a smaller error if I make each of these sites equal to 0, T matrix is equal to 0. If, however, I say this, then I will get what is called a single site representation or the coherent potential approximation. This is 0, no doubt, Ti must be. This is equal to 0, no doubt, each interval. But that this is so true is not quite correct. But if I demand this, then certainly Qi will be 0. Whether let each of these should be 0 on an app. Then this is 0, and if this is 0, then this is 0. So I say single site approximation. That clear? What does that mean? It means that if this has to be 0, then I have CA, TA. So this is an approximation nevertheless. But the expansion helps you to justify that approximation. Okay. Because I is not equal to, at least in this term it is 0. I'm all right. This term is not all right, but it justifies it. We have C and T. But then what is TA? What is TA? Remember, what was their impurity in this case? What is TA? TA is equal to epsilon A minus sigma. Because it was epsilon A minus sigma, but that was the potential over 1 minus. Now let me use for the Green's function. Let me use this function fz. Epsilon A minus. It was G0, you remember? G0 diagonal. So that is what it is. What is TA? It is the impurity potential over 1 minus the Green's function of what? The Green's function of the ordered so-called effective medium. Okay. That I'm calling, let me call it f of z. I will just write down this expression for you. But remember, it was the G0, it was the Green's function G0, the diagonal part of it. Okay. Epsilon A minus. This algebra is the same as you do it for the single impurity calculation for the cost later. How an operator like TA becomes a matrix like this. Okay, this is basically this is not an operator anymore. How an operator like this becomes a scalar like this. Okay, that expansion you have done for the single impurity problem. But even if you don't remember, if you cannot reproduce it right now, okay, or a unit later, you know that this is V over 1 minus G times V. And at G I'm calling as F just so that I don't get confused between different G's. I will explain what does F means in a minute. Okay, what I mean exactly. But let me use for G0 a quantity like F of Z. Okay. So now let me pause at the moment before I write down the CPA equation. Is there any question?
Yes. So,
who is this? Please identify yourself.
Johnson.
Yes, go ahead.
So I couldn't quite follow when you went from summation over Qi average to average Qi equal to 0 on the left side.
This side.
Yes.
T is just the sum over I QI.
Yes, sir, that's fine. But from there to average over QI equal to 0.
Q2 plus Q3. It's the sum now,
Yes, sir.
right? So each of that sum must be equal to 0. There's nothing to choose one over the other. See, the summation setting a sum, individual sums to be average of individual terms to be 0 for the summation is all right. A product I cannot do. If it is a product like AB, I cannot do AB is equal to A average of A into average of B. For a sum,
We can have something like one of them is the negative of the other some of the other parts, and
that is a very, very odd case. It won't happen, I can tell you, I can show it to you from probability theory. What are the conditions under which this is correct? Let me just do it in another class for you. But it's not as drastic an approximation as this. As this one, for example. This one. This is not an approximation. This one.
so is there some condition like Q, all the QIs are positive definite or something like that?
Maybe or maybe not. I can show it to you the conditions, not necessarily. Basically, these are operators at the moment. So then I have to do what I have to do. I have to decouple it in the one-year representation. After decoupling in the one-year representation, I have to show you that these quantities are all positive semi-definite. Okay. That I have not done. This is actually an operator. When I say the average is 0, I mean I will first do a one-year representation of this and then show. Reduce it. I will do calculate the matrix elements in the one-year representation.
Yes, sir. So and on the right side, when you took the average of Ti, G0, Tj, that's because you're not summing over J. The Ti is not included in the summation over J, right? That's why we can do that.
Yes. A is not equal to I.
Yes.
These are independent to A. But here, of course, I can be equal to J. Or I know. Like only successive sites are not equal. Not as though all the sites are dissimilar from each other.
Yes.
Right.
So this Chandrasekhar.
Yes.
So, but if J is not equal to I and K is not equal to J in the successive step, then
No,
shouldn't it?
Here, I is not equal to K, K is not equal to J. If I
Okay.
write it like, or if you want, I can write it like this. To be faithful to this. I is not equal to J, J is not equal to K. That is what this expansion means. If you start from here, it would mean that every successive term is not the same as the previous one. But it doesn't mean that the third term is not the same as the first one. Or the seventh term would be equal to the fourth term.
Okay.
That is, if you start from here, you can show it quite easily. Right? Okay.
Sir? Sir,
Who
this
is-
is Saloni. Yes, sir. Sir, so
Yeah.
in the Hamiltonian, we took the transform term as T, which was unchanged, and now we are taking Ti, Tj. So why is it so? This is different, right?
That T, by the way, oh my God. This
Yeah,
T
this is just, we are representing Ti as Vi by 1 minus G naught Vi. This is different, right?
Yes. This
Okay.
T has nothing to do with the transfer term.
Okay, sir.
Term there. This is very standard for the transfer term. Right? For the transfer term, I should have used another thing like hopping or something.
Yeah, I got it.
Because that's an unfortunate choice of symbols. Okay. But this is so standard that everybody now knows that this T means the T matrix and that T means the transfer term. All right. So can I continue? So you have something like this, and you have CA, TA plus CB, TB equal to 0. So the CPA equation, coherent potential approximation, is simply CA silent A minus sigma over 1 minus f of z silent A minus sigma plus CB epsilon d minus sigma or 1 minus f of z epsilon d. That plus this must be equal to so we will carry out just about a 10-minute analysis of this equation so far and some summing up. Okay. So this is going to be my operative equation. Note, I have to explain to you clearly what this f of z is. Okay. And note that the sigma, okay, it occurs in all kinds of places. I can simplify this equation just a little bit by cross multiplying. So what I will suggest is that you also cross multiply and simplify. I also do it. And then you compare your result with me, otherwise you just copy results that I'm writing. Cross multiply and simplify. Okay. So I'm doing it. You too do it. Okay. Cross multiply. And you don't have to do it exactly like I do it. I take the attendance, so you just have to show yourself and say present. That's all. Okay. Where is Akshat Mishra present? Aparna C is present, I can see her. Chandrasekhar Iyer, he's not Chandrasekhar Iyer. Where is he?
So I'm here, present.
There. Ah, yeah, okay. And John Sunil, of course, he has been speaking, so I'm there. Prithvitosh Day is present. Rishabh Verma, where is
Yes,
Rishabh?
sir. Yes, sir.
Saloni Mandaloy. There she is.
Present.
Yeah, Saugandha, present.
Present, sir.
Subhajit Roy, present. Okay. And the other three people are absent, I'm assuming. Krishna Gagdi Shetty, Sukant Chamoli. Who is present? Krishna Gagdi Shetty, sir. Sukant Chamoli.
Sam present.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But one more person should be absent. Pratyush Bhatnagar. How come how many people? One is right here. So, okay. I'm not counting. Take her. Okay, so there's only one person absent, that is Mr. Pratyush Bhatnagar. The others are present. Okay, so again I pin myself to see that. Okay. Wonderful. So are you able to derive this? Are you recording this? I hope you are. Are you able to derive this equation? Yes. All that you do is cross multiply, forget the denominator. That doesn't do anything catastrophic, let's assume. So therefore you get only the numerator and you get sigma is the VCA term, the virtual crystal approximation term, minus this correction term. Okay. Now what is F? What is F? F of Z, okay, is supposed to be 1 over n sum over k 1 over z minus s of k minus sigma z. Okay, that was the ordered medium. You see, ordered medium has a sigma z. Instead of epsilon, there is sigma z. What is this s of k? S of k is the log representation of minus t, the transfer term only. So s of k, for example, in one dimension would be equal to minus 2t cos k. Okay, because that is just the t term. Okay, and this is the sigma. So you see where I'm caught. You see what's going to happen. I have a sigma. Okay, that sigma is right here. That will just give you at most a quadratic equation. But if I have an f which has also got a sigma, then you have a non-linear equation in sigma. So sigma depends on sigma square here, quadratic. But look at this, there's another sigma. So you basically get, as you normally do in all mean field theories, you get a self-consistent equation. If you're doing Hartley walk, you have to assume a rho density of the electron, and then you get another density out. Okay. If you are doing, for example, the Weiss molecular field approximation for the Ising model, you have a sigma in terms of a, how should I put it? What is that equation called? In terms of a tan hyperbolic equation, okay. Transcendental equation, which is solved by the graphical method. So here also you have a non-linear equation. So you might. People normally at the simplest level for a single band case, they use the Newton-Raphson or they use the secant method to solve it. So let me make a few comments about this which are very important. Okay, by the way, this can also be written like this. It can be written as integral rho 0 Of course, you can write it in terms of the density of states, let's say. Rho 0 z minus sigma, z prime minus sigma over z minus z prime. Okay. When the rho 0 z prime, okay, is basically, this rho 0 refers to this s of k. So, it is essentially what you would get is basically, if you know, if I don't, you normally get something like z minus z prime minus sigma, but then I define the z prime in a particular way and I get z prime minus sigma. You want me to show you this or are you comfortable with it? Take a look. So, if you're not, then let me know to think about it. This is what is rho 0 will be for? It will be correspond to this, it will be like this. Rho 0 will be nothing but 1 over square root of 1 minus z prime. Anyway. That is what f of z is. If you are still confused about it, I can show it to you next time. But just think about what f of z. And the other thing would be to make a few remarks about this. So it is basically, first of all, it is an effective medium theory, or what is called a mean field theory. Remark number one, it's an effective medium or mean field theory. And this is where I need some of my notes because I shouldn't forget some comment about this. And basically, You assume sigma. Get f of z by this expression. Then from f of z you get sigma. You can do an iterative process. To solve this problem, you first have to assume some sigma. Maybe you can assume the virtual crystal. You get f of z. And again, when you solve this equation, you get a new sigma out. So you basically do it by non-linear. Third thing is it is independent of dimensionality. It doesn't depend even 1 or 2 or 3 dimensions. Whatever density of states you feed in, okay, you get out. So whatever density of states it is, it does not essentially depend on whether it's a square lattice or it's how should I say, it's a zinc blende lattice or a diamond lattice or whatever. You just give me the goddamn density of states by experiment or whatever, and I will get you. So it's dimensionality independent. That also happens, for example, in the Ising model. In the Ising model, when you do the mean field approximation or the Weiss molecular field approximation, what you will get is a result which is actually only depends on the number of nearest neighbors. Whether there are 20 of them, 2 of them, or 10 of them, it doesn't matter. It's a dimensionality independent result. Or it is symmetric. If you interchange CA and CB, and at the same time, if you interchange epsilon A and epsilon B, you'll get the same result. Look at this expression. I hope I'm not, here it is. If here, for example, if I change CA, epsilon A, and CB, epsilon B, I get the same epsilon bar. And here also it doesn't make a difference. If I make it epsilon B here and epsilon A here, I get the same. The CPA is non-linear, yes, but it's very symmetric under the interchange of A and B atoms. Let me see, I may have forgotten 1 or 2 comments, but I shouldn't forget to tell you. Of course, I should have said it right in the beginning, it's a single site approximation. That is what I've said is the individual T matrix is 0, okay, and not the total T matrix. And the last but least, not the least comment that I have to make is the following, that the sigma that you get, even if it's a quadratic equation, and if it does, this f does not depend on, even if it didn't, you could still get a complex solution. So the sigma of z. It need not be real. See, in the virtual crystal approximation, the sigma is just epsilon bar, it is real. Okay. But the sigma can now be complex. That has very important implications. One is that it will allow you to understand when you will get a split band and when you won't get a merge, and when you will get a merged band. Although that this remark will not make sense to you right now, it will allow, it has a certain power behind it. The other is that this sigma is complex. There is no such thing as a band structure. Okay. You have an ordered medium. An ordered medium Bloch's theorem is valid. But in this Bloch's theorem, one of the quantities that sigma or epsilon, which was their diagonal term, is complex. Okay. So if it is real, okay, it has one meaning, but if the band is complex, it means that the states are decaying. Okay. So that's another important implication. So I think with this, and there's one other remark that I want to make, I would like to end today's lecture. What are we going to do next time? we are going to explore the CPA. We'll explore ramifications of the coherent potential approach. You will see what it means actually. If I have to do an actual calculation, what will I get? Okay. How do I go about looking at it? How do I convince myself that this is right? And this is a great approximation. Besides just saying that it has got a very appealing idea behind it, that is that the T matrix should be 0. So we will explore the equation next time. But there's one side remark I want to make, which will probably, I don't know why everybody is calling me today. Hello? हाँ हाँ कर लीजिए. Okay. So basically, I hark back to the fact that I had a T matrix which looked like this: sum over I, Pi plus Pi. That is how the T matrix looked. Right? What does this mean with a bar, with a prime? It means that when you sum over I and j, etc., no successive indices are equal to each other. So I could write this as some Pij, just taking nearest neighbor, the first side and the last side, and everything else in between is summed over. This thing, which I have not done, I've done a single site approximation. This thing is something that you need if you're doing amorphous systems. Because when you're doing amorphous systems, you need to average this. Okay. Why is that? Because in amorphous system, there is no lattice. So what you have is an atom here, and there is an atom here, and then there's a probability given by a pair distribution function, or a probability function which tells you what is the probability of finding an atom over here. System, if you're doing a liquid metal disordered system, then in that case, there is no way you can get around with just single site. You need to have two sites. Okay, there's one site here and the probability of having another site there. In that case, what happens? You can do some kind of an averaging there, but there's nothing to set. There's nothing that you can set equal to 0 there. Okay, when you do that averaging, first of all, this is called the path operator. Yeah. This path operator is due to geography. It was exploited by geography and independently by Roth. So I think the person who really understood it correctly, the situation for amorphous system, was Professor Laura Roth, because she realized that here you cannot do just a single site approximation. You have to do a path operator approximation. Because you have one site here and there's the probability of another site there. So in that case, although we are not doing it yet and we may not even do it in this course, okay, you have to remember that there is something else that happens there. The single site approximation is something that Mel lacks. And he told it to two postdocs. So he told it to two guys who were postdocs at that time in 1967 in Bell Labs, Paul Sauven and Dave Taylor. And for electrons, the coherent potential approximation is credited to Paul Sauven, and for phonons, it's credited to Taylor. So that's how it happened. That's the history. But Lax had this single site in 1952. In fact, I would say that he had this idea anyway. He knew what is a CPA, but he just didn't want to sit down and write a paper about it. So that's what happened. Sauber and Taylor, they get all the credit. If you want to understand the single band thing that I have done here, okay, and the single band, there is a nice paper 1 year after Sauber, okay, which actually does it does all the asymptotic limits also. And I would urge you to take a look at that paper. It is by Velichky, Patrick, and Aaron Wright. Okay, it's in Fitzgerald, 1968. At that time, there was no Fitzgerald A, B, C, D, etc. That started only in 1970s. Okay, 68 there was only a Fitzgerald. Physical review. I forget the exact reference. But it's a famous enough paper. It's a long paper that will have all these, several of these details. So in 1952, Mel Lax had the so-called T-matrix expansion. 67, Sauber and Taylor sort of developed this PA. Velichky, Kirkpatrick, and Erlich really explain it to all of us by using a single band Hamiltonian substitutionally disordered system, and then they work it out through. Where was Mel Lax? Mel Lax was at City University, and he was a consultant in Bell Laboratories. These two guys were postdocs in Bell Laboratories. Okay. These people, Henry Ehrenreich is a very famous person. He's from Harvard. If you look at the sites and Turnbull volumes, solid state physics volumes, there are at least 30, 40 of them now. Okay. The volumes, one of the editors is Ehrenreich. For a long sites Turnbull, our sites Turnbull and Ehrenreich. Same Henry Ehrenreich of the sites Turnbull volume solid state. Kirkpatrick, of course, was either a student or he was a student of Ehrenreich in Harvard. And then he went on to what should I say? IBM Watson. IBM Watson Center in New York State. And of course, he is more famous now for having developed used the Metropolis algorithm to design VLSI chip. So it's famous for something else also. Besides this paper, which is a very well-written paper. And Velichky is the most interesting of all guys. He is the guy who really understood the CPA very well. Okay. And Velichky was Hungarian. He had been called on a special, those times, I mean, the Cold War was on, but Harvard and some other places had this program of scientist exchange. So Velichky was visiting Harvard from Hungary, okay, for about a year when he developed this. And I think when he went back, I think they would not allow him to come back again for a long time. So he is really outstanding. So that's the history behind this. Some very colorful and interesting history. Famous for the Metropolis algorithm. Famous anyway, and Ehrenreich famous for the sites in Turnbull volume. Mel Lax, of course, I think all of these people are known. At least Ehrenreich and Mel Lax are no more. Right? Dave Taylor was Canadian. He went back to Canada after his postdoc. So that is the history and geography. We will explore the CPA equation next time. Thank you. If there's a question, I can address it. Okay. Okay. You can, of course, there are some projects I would like to suggest after tomorrow, next time. and you can take it up. I think I will just assign you the project. There is no choice. I think all of you are present except for, I think, one person, Pratish Bhatnagar, who is absent. Any questions? Was the lecture clear? I mean, was the blackboard visible? Yes or no?
Yes, sir. Visible.
Is the yellow chalk better than the white, or the white is better?
And you can't really differentiate between the two. So
Okay, very good. All right, you can turn the recording off.